Hello, this is Dr. Wuki, and welcome to the fourth lecture series on this chapter, that is chapter 14 on acids and bases. So we'll begin this chapter with talking about salts. What are salts? Salts are basically ionic compounds, that is a general name for ionic compounds, and they dissolve in water to form the two ions, the positive ions and the negative ions. And the ions are considered to be independent in their freedom of movement in dilute solutions. And these can behave as acids or bases under certain conditions. So, very important to know the properties of salts in that respect. There are salts that, when dissolved in water, that contains cations of strong acids and strong bases, they basically have no effect. So, salts that produce neutral solutions come from the strong acids and strong base. And that means when they dissolve, they give a pH of 7, neutral. Examples, you have potassium chloride, sodium nitrate, and potassium nitrate. Now, if you look at these salts, they come from a strong base. The strong base is, this one is KOH. This one, strong acid, it comes from HCl. Strong base, strong acid, and you can do the same for all this, and you'll find that it basically comes from strong acid and base. Now, a basic solution is formed if an ion of the salt is a conjugate base of a weak acid. So when you come from a weak acid, this is where the situation is going to change. A weak acid will produce a base, which we call its conjugate, as conjugate base, that can interact with water. That interaction meaning a reaction. And that sort of reaction is often regarded as hydrolysis, which I will probably mention later on. But let's look at a conjugate base. When you have a conjugate base formed, it is going to behave like a base. So what does a base do? It will attack water and form the conjugate acid and its conjugate base pair. So here you will have to look at the Kb value. So although you have a weak acid to begin with, because of the relatively strong conjugate base, you're going to work with the Kb. So this relationship here is going to be really, really important. Meaning that we may be dealing with the weak acid, but in the formation of the salt, we are going to revert to find the base. Okay, let's look at this example here. Sodium acetate. Sodium acetate is a salt, and it comes from a strong base, weak acid. Okay, strong base is this one here, sodium hydroxide. Weak acid is acetic acid. So let's look at the pH. That's the example here. But let's look at one example of calculation here. So a pH of sodium fluoride. Sodium fluoride is a salt from a strong base. This is strong base, sodium, and this is weak acid. Okay, weak acid is coming from where the F is coming from. So when it's a weak acid, we look at HF. What is the Ka value for HF? Ka value is given 7.2 times 10 to the power minus 4. So often that is what is given in the table. Now, in order to do this calculation, because when a salt is formed, the concentration of the salt will be the initial quantity that you have been given, and whatever that concentration is going to be, what will the initial concentration of this F minus. Now, as we say, this conjugate base is going to attack water, which is what I call hydrolysis, meaning splitting the water molecule. It'll attack water and it'll form HF, so it will take one proton and form the base. So in other words, the hydroxide, which is a strong base, is going to be the sort of net species that is formed in this salt reaction. Okay, so this yields the following Kb expression. Kb is equal to HF times OH divided by F minus. That's what we get. And let's look at the value. So that's the value. Ka is what we know, and Kw is also known. So you get your Kb. So notice now, when you have the Kb, we can set it through the ICE table. So 0.3, the initial, and 0 and 0. We are assuming that no or minimal contribution from the other equilibrium, that is in water. So change minus x plus x plus x, and then you do the usual equilibrium setup. Now let's look at the values. So Kb is equal to that, and these concentrations, now you can substitute in. Again, we can apply the approximation here, and you come with a value of x. So x is 2.0 times 10 to the power minus 6. And notice now that will be the concentration of OH and also the concentration of yes, of these two, HF and OH. Okay. So that will be the OH concentration, and you can find the POH, then you can find the pH from taking the difference or subtract it from 14. So as expected, we see now that this acid, this salt here, NaF, is essentially basic, and that's what we are talking about. So salt that comes from a weak acid becomes basic. Okay, let's consider the dissociation of hydrocyanic acid. Hydrocyanic acid, this is the equilibrium, and it shows that Ka is 6.2 times 10 to the power minus 10. Cn minus, the conjugate base, is relatively strong. When we say strong, that will be compared to what? So Cn minus will hydrolyze water to again form this and release the OH. So we can find the Kb expression, Kb, Kw over Ka, that gives 1.6. Now if you see this, 1.6 times 10 to the power minus 5, that's relatively greater than the usual. I mean, looking at that weak acid value, not as significant, but you look at this base, it's quite a strong base, which is almost to the order of 5. order of magnitude here. So CNs appear to be weak base when cyanide ion reacts with water. It competes with the hydroxide of H plus instead of competing with water. And that's the relative strength. You see here the strength of hydroxide is greater than that of cyanide ion than that of water. So you will see here that it's relatively stronger than the water. What about the other type of salt? Salt that produce an acidic solution. And you might have guessed, if we have a salt that comes from a weak base, this is going to give us an acidic sort of solution. So let's consider a salt that comes from a weak base, ammonium chloride. Why? Because ammonia is a weak base, chloride comes from a strong acid. So you can see here that this is coming from a weak base and a strong acid. And we'll look at this other example later on, and that is aluminum chloride. So aluminum chloride, again, you can look at that in terms of a weak base, coming from a weak base and a strong acid. One other point for the metal ion is that the higher the charge on the metal, the stronger the acidity of the hydrated ion. We will look at that. Okay, calculate the pH of 0.1 molar NH4Cl. Now, if you look at this salt here, it will dissolve completely to give you concentration of NH4 plus and Cl minus. Now, because of the conjugate base of this is going to be strong, we will have to consider the Kb value, and that is Kb value of this NH3. So let's set up this calculation. So this is the dissociation. This is the dissociation reaction of NH4 ion. It will lose a proton and form that weak base. And so Ka for this is NH3 H plus divided by NH4. That's the ionization constant of the acid, because this is the acid species. Note that although the Kb value for NH3 is given, the reaction corresponding to Kb is not appropriate here. The reason is that NH3 is not the major species. We are looking at NH4 because it is a salt that will be formed. It's coming from the, instead of given the value of Kb, is used to calculate the Ka for NH4 from the relationship. So Ka is equal to, Kw is equal to Ka times Kb, and then we can find Ka. Ka is that term. And substituting in the values, 1.0 times 10 to the power of minus 14, 1.8 times 10 to the power of minus 5, and then that gives us the value of Ka. Notice now that we have the Ka of NH4 plus. NH4 plus. So although NH4 plus is a weak acid, as indicated by the Ka value, still stronger than water. So in other words, it's going to be able to compete with water on that. Thus, when we are looking at this, it was going to change the outcome of the pH. So we can work out the equilibrium quantities by working out the ICE table. So draw the ICE table of ammonium ion, and set the initial which comes from the dissociation of the salts, 0.1 molar. We assume 0 in this case from other sources, and this will be the major, and that's ammonia. Change minus X, and the equilibrium concentration will be 0.1 minus X, X, and X. So bring in the values and substitute. 5.6 times 10 to the power of minus 10 is equal to X multiplied by X over 0.1 minus X. Again, we can use this approximation step, assuming X to be very small, and that will lead us to this, which helps simplify the problem. We can now solve for X. Now, when we get the value of X, this is the concentration of H plus and also the concentration of NH3. So we can now work out the pH value. There we go, pH value of 5.13. What do we see here? It's less than 7. So in other words, the salt of a weak base becomes acidic, and vice versa. The salt of a weak acid becomes basic. So for pH less than 7, that's acidic. pH greater than 7, that's basic. pH equal to 7. So if Ka is greater than Kb, that'll be acidic. Kb is greater than Ka, that'll be basic. So we can do a very qualitative sort of judgment using the Ka values of a species that are involved. Predict whether the aqueous solution of each of the following salts will be acidic, basic, or neutral. So let's take this one. This comes from a weak base and weak acid. Weak base and weak acid, what would you expect? That should be, so if you look at the Ka values, Ka for NH4 is 5.6 times 10 to the power minus 10, and Kb for acetic acid is 10 to the minus 10. What do we get? Pretty much they neutralize each other. So they are same Ka value and Kb, sorry, K value and Kb. So that means they cancel each other out and you expect a neutral. Okay, let's look at that second one. NH4CN. Ka value for NH4 is 5.6 times 10 minus 10. Kb value for CN is 1.6 times 10 to the power minus 5. So you can see here that Kb is a lot greater than Ka. So Kb is greater than Ka will be basic. Okay, let's go on to the next discussion, and that is the effect of structure on acid-base properties. Looking at the structure of acid-base, factors that determine whether a molecule containing HX or X2 bonded to hydrogen behaves as a Bronsted Bronsted-Lowry acid. This one is dependent on these two factors, the bond strength and bond polarity. So classes of acids we want to look at are the hydrogen halides or halide acids and hydrogen metal ions. Now let's look at the hydrogen halide acid and look at the bonds for this series. HF, the bond strength is 565 kilojoules per mole. Now as you go down the group, you see the decreasing in bond strength. So these are all relatively same group of acid, but notice the strength. This 3 at the bottom is strong, this is weak. Now one of the reasons you can see that because of this strong bond. Therefore, it's not easy for the water to break this bond up. So the hydrolysis or the breaking of that acid is not as easy compared to these ones here. Okay. Acids that contain oxygen, that is, when they have the oxygen that is bonded to the acid hydrogen, then X value. For a given series, the acid strength increases with the increase in the number of oxygen atoms. So let's just look at this one. You can see here that as you increase the oxygen number of oxygen atom bonded to the central atom, you increase the acid. So here is very large, 10 to the power of 7. Here with how many oxygen? 1, 2, 3, 4 bonded to the central atom. Here is 3 bonded to the central atom. 1 is the Ka value. Here there is 2 bonded to central atom. 1.2 times 10 to the power minus 2. And you can see here. So you can see clearly that the strength of the acid increases as you increase the number of oxygen atoms bonded to the central atom. So the same observation is seen here. You can see that number actually increases as we go, as we increase the number of oxygen. Now, if you look at the H oxygen X bond, if you look at this, you can see the trend too. When you have a high electronegative group, the acid strength is high, the highest, compared to the low electronegative group. So here the electronegativity decreases from chlorine to iodine. So that's why I have that decrease in the acidity. And so as this one, that's very, very weak. Electron withdrawing, these are all electron withdrawing group, is very weak. So that's why you see the acid is very, very low. Now in anhydride metal ions, these are acids, and they exhibit behavior similar to oxyacid. The greater the charge of the metal ion, the more acidic the hydrated ion becomes. So which factors below determine whether a molecule containing HX bond will behave as a Bronsted-Lowry acid: strength of the bond, length of the bond, polarity of the bond. So the solution here is these two: strength and polarity of the bond. Okay. Now, in general, this is what we should expect when we are looking at the acid-base properties of oxides. Non-metal oxides, meaning these are covalent, pretty much covalent compounds. Okay, covalent compounds, SO2, carbon dioxide, NO2, these form acidic oxides. They lead to the formation of acidic solution. That's why carbon dioxide, when it dissolves in water, it becomes acidic. So as these other two. Now, for basic oxides, this one comes from metal. So non-metal in the previous one, this one's a metal. Metal oxides, they form basic oxide. Why? Because when they combine with water, they form hydroxides. And these hydroxides are basic. So this will form calcium hydroxide, this will form potassium hydroxide in water, and that results in the basic solution. Okay, that leads us into the final model for describing acids and bases, and this is known as the Lewis acid or Lewis base model. Now, this definition here is very encompassing. In other words, it covers pretty much what we have discussed from the Arrhenius definition and also Bronsted-Lowry definition, including what is not covered by the two. So this one is defining an acid as an electron pair acceptor and a base as an electron pair donor. Now you look at these definitions, they are all important, and that's why we continue to use and apply them. But you'll see that the Lewis definition really covers the entirety of all the other two that we have looked at. So what does it mean? In Lewis acid or Lewis base, you can look at a system such as this. So here is a Lewis base, which is an electron pair donor. This is an electron pair acceptor. And that forms this molecule. Now, this reaction here is well defined by Bronsted too. Well defined by Bronsted, because Bronsted says this one is a proton acceptor and this one is a proton donor. So Lewis and Bronsted both okay with this. They define that pretty well. Now in here you will see that Bronsted really doesn't show much of an indication to describe this. So here this is an electron pair. This is electron deficient, because if you look at the structure boron, there are only 6 valence electrons. So it will accept 2 pairs of electrons to complete its octet. And that's why this acid here and base reaction is only best defined by the Lewis definition. So this is an electron pair acceptor and this is the electron pair donor. And then we form this complex molecule. And likewise, when we are dealing with metal ions is not easily categorized as acids or base, but using the Lewis definition, they clearly show as an acid. You can see here that they are electron pair acceptor, and that's why the ligands or this electron pair rich molecule like water, they can provide the lone pair for the positive charge, and that will form the complex, which is what we call the hydrated metal ion complex. So this is an acid-base reaction based on the Lewis definition. So this is another example. You can see here in SO3, the reaction with water is a typical Lewis acid-base reaction. The electron pair comes from the water and sulfur accepting the pair of electrons. And let's just finish up with these two examples. You can see that nickel react with ammonia to form the complex. So which one is an acid, which one is a base? Look at that. Nickel 2+ accepts the electron pair from the ammonia, and that will produce the complex. Now, in terms of the number of ammonia it complexes with, that's really not in our position now to go into more detail, but that's what we see. This is what we see in normal complex ion chemistry. It has that 6. And why is the 6 common? I'll just mention this because it forms a stable octahedral complex. And you're already aware, you already know what an octahedral complex is. It has 6 bonds to the central atom, and it forms that octahedral structure, which is very energy favored. So that's why you see the 6 in this number of molecules that attach to the metal ion. Okay, that finishes off the fourth and the last series of videos lecture on chapter 14. Thank you for listening.